So if we look at the processes that are spontaneous in the previous video, what we saw were there are things that tend to lead to an increase in disorder, and I'll put that in quotes. It's a very non-specific term here, but our molecules are spreading out, right? They're taking up the space that's available, or the ordered all gas on one side, all gas on the other, they're dispersing and diffusing between each other. And so we want a way to quantify this. And ideally this would be a state function, so that it doesn't matter which process, how the process is occurring. So what we can look at is one thing that sort of is related to disorder is heat, right? As heat propagates through a system, it leads to things moving around in a more disordered way. But that's not a state function. But let's look at a heat transfer. So if we're thinking about an ideal gas and a reversible process in an ideal gas, we can use some of the equations we developed for the first law to define this. So reversible transfer of heat for an ideal gas. And though we're going to be looking at an ideal gas, what we derive will apply generally. So the reversible transfer of heat is going to be equal to delta U minus the reversible work that's done in the system, since we're looking at a reversible process. And we saw from the previous chapter that we can define delta U as our heat capacity at constant volume times our change in temperature, CV dt. And the negative of the work will be plus PdV, right? So work is minus PdV. So then we have our two terms here. So CV dt is just going to be what it is. CV is some constant for our system. And we can substitute the ideal gas law for P, so nRT over V dV. Okay, so we have a term here that this is only depends on temperature, but our term over here has temperature and volume. So dq here is not an exact differential because we don't have one thing that just depends on one variable, another thing just depends on another variable. So that's where we have to write with this inexact squiggly d. But what if there was a way we could rewrite this and make it so that temperature was only in one term and volume was only in a different term? Then we would have an exact differential. And so what we can do is divide through by temperature. So divide by temperature for the whole equation. So we'll have dq reversible divided by temperature is going to be equal to CV over T dt plus nR over V dV. And now we have this term only depends on temperature. This term only depends on volume. This is assuming, of course, of a closed system, so the n doesn't change. And now this is an exact differential. And so this is what we define as the entropy. And we call this ds. And this is our definition here. The change in entropy is equal to the reversible heat change in a process divided by the temperature. And because it is an exact differential, this is a property of state functions. So this means that S is a state function. And so for a cyclic process, our change in entropy is going to be equal to 0. Another way of writing that mathematically is if we have an integral of ds over a circle, that's what this circle here represents, is equal to 0, just like it would be for delta U or delta H, right? If we go, say draw a PV diagram, if we imagine up whatever path we want, if we go from 1 to 2 to 3 back to 1, as long as we go back to 1, we're always going to get back to our original value, so the overall change is going to be equal to 0. Now, the important thing to remember here is this, I'll highlight in red, this is the reversible heat that's part of this. So even if the process itself that happens is irreversible, the entropy is defined as a reversible process. So as long as we can imagine up a reversible process that does the same thing the irreversible process does, we can find the change in entropy because the path doesn't matter. And so we'll look at one example of finding the entropy for a process involving ideal gases. We'll look at some more of these in class as well in the next video.